Okay, fundamentally, an exponential function is a very specific type of function. It describes a lot of things in nature, science, and finance. An exponential function is any formula that can be put in this format. Y equals a times b to the x. Now, when we talk about an exponential function, it has four components which you should always be able to identify by looking at the formula. It has an input variable, an output variable, and two constants, a and b. Our main interest, well, not our main interest, but one of the things we need to clarify is what those constants, a and b, do inside the exponential function. Now, let's take a look at a basic exponential function to see what I'm talking about. So this is an exponential function because it follows the pattern, a constant times another constant raised to my input variable. Now, let's take a look at plugging in some data from this formula. Starting with plugging in 0 into this formula, I end up with y equals 2 times 1.3 to the 0. Anything raised to the 0 is 1. So this simplifies to 2. Notice, that was in the location of my a the whole time. When I plugged in x to the 0, it had no impact on my a because everything else became a 1. So this is referred to as the initial value. But when I start plugging in higher values, next value I get is 2 times 1.3 raised to the first, and I just take my 2 and multiply it by 1.3, and I get 2.6. Next y value I get by plugging in a 2. And notice what happens. I'm going to just multiply by that 1.3 2 times now instead of 1 time. So 2 times 1.3 squared is 3.38. However, notice I could have just as well taken this 2.6, got directly to this 1.38 by multiplying by this number. The name we have for that number is called our factor. And the way an exponential function works is we start off with an initial value, and we get to the next location on the table. As long as my input is increasing by 1 unit, the next location on my table is going to be found by multiplying by that factor one more time. Now, let's take a look at something like this. Here was an interesting question my algebra teacher asked me, or asked our class. Is there anyone willing to take $10,000 every day from me, and all I ask back from you is 1 penny? However, The next day, I'm going to give you another 10,000, and you're going to give me 2 pennies. On the third day, I will give you another $10,000, and you will give me 4 pennies. I will give you $10,000 a day for 30 days. You will give me 1 penny, then 2 pennies, then 4 pennies, and you will follow that pattern for 30 days. If you start, you have to agree that it has to go all 30 days. What he was proposing was, on one side, you get 10,000 every day. You would get that 10,000 for a total of 30 days. So, actually, it'd start by giving you 10,000 and then giving you 10,000 1 day later, 2 days later. So you'd actually get a total of 30,000 for initially, plus 30 more days. So it'd be 31 times that you would get the $10,000. That would be a total of $310,000. Starting today and for 30 more days in the future. What you have to give is a penny. So let's take a look at this formula I wrote here. Notice, when you plug in a time of 0, I have that 2 raised to the 0, which is a 1. You have to give exactly 1 penny back. Next day, plug in a 1. I'm going to take this initial value and I'm going to multiply it by the factor to go 1 step on my table. So we go from 1 penny to 2 pennies the next day on day 1. Well, 1 day from now. 2 days from now, to get to the next point, notice by plugging in a 2, I'm multiplying by that 2 twice. I've already multiplied by 1 time, multiply it again, and we get 4 pennies that you have to give back. So you've gotten $30,000, and you've had to give back, what, 7 cents so far? Seems like a reasonable deal so far, yes? Next day, you have to give back 8 cents. Next day, 16. Next day, 32. Next day, 64. Next day, 128. Next day, 256. Next day, 512. Next day, $10.24. Seems still like a pretty reasonable deal. In this, starting at initial day and then 10 days in the future, you've received $110,000? And you've given back maybe, I don't know, $20? The next day you'll have to give back how much? $20.48. But let's see what's happening here. If I use my formula directly for day 25. So now, I'm going to pull out my calculator, take 0.01 times 2 raised to the 25th. Oh wow. It's grown quite substantially, yes? You're going to have to give back 335,544, just round to the nearest dollar. Oh, wait a second. On all 31 days, you're only going to receive on all 30 days, you're going to receive a total of $310,000, right? On day 25, just on day 25, you've given all of that back and more. And we still have a few more days left. Those last few days can be quite shocking. Let's take a look. Day 26. Day 27. 1,342,000. Day 28. Day 29. Day 30. On the 30th day, you'll have to pay back $10,737,418.24. Doesn't seem like such a good deal anymore. No? Exponential functions. The power behind an exponential function is time. If it's getting bigger, it's going to keep getting bigger faster. Each and every time, every single step is going to get larger and larger and larger. Very different than a linear function. Very, very different than a linear function. And what we have to look at when we're talking about exponential function is, how do I wrap my mind around how fast it's going to grow? That all comes into play from the factor. We call the factor b is what's going to determine just how fast an exponential function grows. So we kind of have to wrap our mind ourselves what it means to make something grow by multiplication. First of all, there's one number I can multiply by over and over and over and not get any change whatsoever, and that's the number 1. No matter what I multiply 1 by, I always get the same number, and I can multiply that number by 1 again, and again, and over and over and over, and nothing happens to it. So the only value that the factor cannot be is 1. Because when you multiply by 1, nothing happens. To make a different value with multiplication, clearly then I must multiply by something different than 1. Let's talk about multiplying by something like this. If this is my factor, the number that it is amount bigger than 1 we call our rate. So this number is this much bigger than 1. Now, another way of writing that it's 0.2 bigger than 1, I can also say that it is 20% bigger than 1. If I take a factor that looks like this, this factor is going to cause my function to get bigger and bigger because I'm multiplying by a number bigger than 1. As long as I'm multiplying by bigger than 1, it's going to cause my function to grow. This factor is this much bigger than 1. Another way I can write that is it's 5% larger than 1. We refer to this number as our rate. And we can write our rate in 2 different ways. Notice both those numbers have the same meaning, so they're both the rate. 0.2 is 20% larger than 1. 0.5 is 5% larger than 1, so I'm always going to call that value, no matter which way, the rate. But one's in decimal form, one's percent. The one in decimal form looks smaller. If I want to talk about rate, I'm going to use the letter R, because it's the first letter in rate. But I'm going to use a little r in decimal form, because 0.2 on paper appears smaller than 20%. So the rate in decimal form looks little, rate in percent form looks bigger. This is my little r, this is my big R. So when I look at an exponential function, I can get an idea how much it's going to bend based on how big the factor is or how big the rate is. Now, let's look at some other factors. Let's look at a factor of 1.7. First question, how much bigger than 1 is this? Or let's take a look at that. Little r, big R. As my factor gets larger, let's look at the factor we were doing on our formula with the pennies. The factor was 2. How much bigger than 1 is that? It's 1 bigger than 1. As a percentage, little r, big R. I'm asking the question how much bigger than 1 the factor is. The factor can be as large as one can imagine. This is a factor of 5. 5 is 4 bigger than 1, or as a percentage, it's 400% larger than 1. All I need to determine my rate is know how much bigger my factor is than 1. Now I can write a formula for that, but it's pretty simple. What is my formula? The little r, which is always calculate first. If it's bigger than 1, all I have to do to get my little r is take my factor and subtract 1. 5 minus 1 is 4. 2 minus 1 is 1. 1.7 minus 1.7. That will tell me how much my factor is bigger than 1. That's called a growth function, and my r is called a growth rate. Okay, so I'm going to take a look at this function, and I'm going to identify the 4 components of an exponential function. The four basic components of an exponential function are the input variable. In this case, my input variable is x. The output variable, which is, in this case, f of x or y. Those values are clearly not the factor. Now, my initial value I will find by plugging in 0 for x. Plug in 0, anything raised to the 0 is 1. The fourth number is called our factor. So I've got 4 components: input, output, initial value. My factor is 1.17. This is a growth function because my factor is bigger than 1. How much bigger is my factor than 1? Either 0.17 bigger than 1, or it is 17% bigger than 1. We can express it in either way. here I have another exponential function. And this one looks a little bit different. I know it's an exponential function because my exponent is the input variable. That's what determines whether it's an exponential function or not. So I've got my input variable is x, so I'm going to identify input and output. It's my input and my output. I'm going to identify my initial value. You need to be a little bit careful here. I'm going to identify my initial value by plugging in 0 for x. 0 divided by 3 is 0. 2 raised to the 0 is 1. 1 times 50 is 50. There's my initial value. There are four and only 4 components of an exponential function. Input, output, initial value. The fourth component we always call the factor. So this factor is not 2, it is 2 to the 1/3. I have a cube root here. I still need that cube root here when I'm describing the factor because that cube root is not part of my input variable. So, my factor is 2 to the 1/3. I'm going to plug that in my calculator and get a decimal approximation. 2 raised to the parentheses, or this, my calculator doesn't need it, 1/3. Your calculator may need a parentheses around that if you have a caret symbol. Enter 1.2599. So I will round 1.2599 for right now. And now I'm going to talk about my rate. My rate is the amount that this is bigger than 1, approximately, because I rounded 0.2599, or big R, it is 25.99% bigger than 1. Got one more exponential function here. I know it's an exponential function because my input variable is an exponent. So because of that, I'm going to identify the 4 components of my exponential function. It has the input variable, x, the output variable, either f of x or y. Notice, I have a negative there, it's still there. My output, y or f of x, is over here. If I was to plug in a 0 for that x, negative 0 is still 0. 1/3 to the 0 is 1, times 500 is 500. I have identified 3 of the 4 components. The 4th component then must be the factor. In this case, my factor is 1/3 to the negative 1.
So the input is not negative x.
The negative is going to stay separate than the input variable, leaving me as part of the factor. 1/3 to the negative 1 is 3. 3 is 2 units bigger than 1. My rate is either 2 or 200%. So we have been talking about growth functions, and they're getting bigger because I'm multiplying by a number larger than 1. A decay is also an exponential function, and the only difference between a decay and a growth is the size of my factor. For a decay, the factor must be less than 1, but my factor still has to be positive. So my factor is going to be between 0 and 1. Let's take a look at this. Here's a function. I'm going to identify my input as x, my output as my y, or f of x. I'm going to plug in 0 for x. 1/2 to the 0 is 1, times 256 is, in this time, my factor then is everything I have not circled. Another way of writing that is 0.5. I'm going to describe my rate pretty much the same way. Even though it's smaller than 1, I'm going to ask the same question. How much smaller than 1 is it? Instead of how much bigger than 1, the question now is, how much smaller than 1? It is this much smaller than 1, or 50% smaller than 1. Let's see what happens with a decay function. I start off with that initial amount, and every time I multiply by 1 more on my input, I'm going to take my output and multiply it by the factor. This is a factor of 1/2. Half of 256 is 128. It's going down. Half of 128 is 64. Every time this goes up by 1, this is multiplied by 1/2. 32. But notice, I'm still multiplying by positive number. So it is a positive number times a positive number, which is always going to have an answer that is positive. It's going to get smaller and smaller, but it's still going to stay positive.
Supposedly it's not very much zero, right?
Exactly.